Hola, hi, this is Al, your statistics instructor. In this video, we will talk about an example that involves a random variable with a geometric distribution. So let's get to work. So this is the problem that we're going to be solving together. Okay? So in this case, what we're given is the probability of an engine malfunctioning. Okay? And what we want to do is finding the probability that a given engine will survive 2 hours. Okay? So one way of finding that probability is remembering that there is a random variable, right, that computes, that gives you the probability of your first success after n trials, okay, n independent Bernoulli trials. And such a random variable is the geometric. Okay, so that guy is the probability mass function, right? It's the formula that gives you the probability of observing your first success after exactly y trials. Okay, which makes sense, right? Where the probability of success is p. So what you have here, q, is going to be the complement of p. So q is 1 minus p. So if you have 1 minus p to the y minus 1, what that means is that the first y minus 1 trials were failures, and the yth trial resulted in a success. Make sense? So what I claim is that we can use that random variable, geometric random variable, to solve this problem. Okay, because we could think of each of these 1 hour periods as a trial, right? This probability would be the probability of success. In this case, the probability of success represents the probability of an engine malfunction. Okay, so what we want is the probability that the engine will survive 2 hours, right? So that it takes more than 2 hours to fail. Make sense? So first, we're going to try and solve this problem. We're going to find that probability by hand, and then we're going to find it using R. Okay? Okay, so let's set it up. So let y be a number of 1 hour intervals or periods of time until the first malfunction. Okay, so if we assume independence between those 1 hour trials, right, and p, the probability of success, is the probability of a malfunction, p is going to be 0.02, right, then y has a geometric distribution with that probability of success, that parameter 0.02. the probability that we want is the probability that the engine survives 2 hours. Okay, so using y as the number of 1 hour intervals, 1 hour periods until the first malfunction, since we want that probability of surviving 2 hours, that is equivalent to the probability that y is greater or equal to 3, right? So if y is 3 or 4 or 5 or so on, that means that the first malfunction took place after, right, the first 2 hours. Make sense? Okay. So remember that let me go back here to the expression of the probability mass function for a geometric. Remember that this guy, the support for the probability mass function, right, goes from 1 up to infinity, right? So if we wanted to find this by hand, it would be this, the probability that y is equal to 3 up to infinity of, you know, that probability mass function. In this case it would be 1 minus 0.02, that would be q to the power y minus 1 times p, right? Because that's the expression of the probability mass function. Make sense? So we would need to evaluate that series, but there's an easier way, right? We could find the probability that y is greater or equal to 3 as 1 minus the probability that y is less than 3. That's easy to find. Well, easier to find. That's just 1 minus the probability that y is less than or equal to 2. And finally, that would be 1 minus probability that y equals 1 plus probability that y equals 2. So let's use r to find this. We just have to use that expression, the probability mass function for this guy twice. So here we go. First one. Oh, yeah, let me launch r. So probability that y equals 1, right? So that's the probability of seeing a success on the first trial. That would be just 0.02. Agreed? Because it's just evaluating at y equals 1. So you would have 1 minus 1, 0. So you would have only 0.02, right? 0.02. And then the other one would be evaluating at 2, so it would be 0.98 times 0.02. So 0.98 times 0.02, this guy, let me copy paste this guy so we can get our probability. Nope, okay. So 1 minus 0.02, right? This is our probability. Okay. So we did it by hand, just using the expression of the probability mass function, right, and some properties of probabilities, right, the complement. Okay. Now we can do these calculations directly using R, but we have to be careful, okay, because it turns out that the geometric random variable in R, well, the probability mass function looks slightly different because it refers to a different random variable. Okay, so let me type help dgeom. That is going to show you the information about dgeom, which would be the probability mass function. pgeom would help you evaluate the CDF, okay, and rgeom, for instance, would help you generate random numbers coming from a particular geometric distribution. Okay, anyway, so here what I want you to see is how this guy is defined, right? So is p times 1 minus p to the x power, right? And x goes from 0, not from 1, up to infinity. Okay, so what I want you to see here is that this guy, right, the random variable x, is showing you, and it must be mentioned something here, yeah, they must mention it somewhere here, that x would be the number of failures until you see your first success. Yeah, so see, number of failures before your first success. Okay, so that's why the expression for the probability mass function looks slightly different, and that's why the support is different as well, because x represents number of failures, not number of successes. Okay, so just taking that into account, if we're careful, we should be able to find that probability that we found by hand. Okay, so here we go. Let me just yeah, let me write it down here, and then we're going to use R, using R. So now remember that x represents number of failures before or until your first success. Really important that the random variable is slightly different. The probability of success, in this case, well, it's the same, right? We are interested in the probability of malfunction. So anyway, if x equals 0, right, what that means is that the first malfunction occurs during first hour. You guys agree? If x equals 1, that means that the first malfunction occurs during second hour. Okay? And if x equals 2, similarly, right, first malfunction occurs during third hour. Okay, so the probability that the engine will survive 2 hours in terms of x would be the probability that x is greater or equal to 2. Make sense? Can you see it? Okay, so it is slightly different in terms of x. Again, it's because x counts number of failures onto your first success. So in this case, probability that x is greater or equal to 2 is the same as probability that x is, well, that probability is equivalent to 1 minus the probability that x is less than 2, right? And this in turn is equivalent to 1 minus the probability that x is less than or equal to 1, right? And this, just to be really specific, is 1 minus the CDF of the random variable x evaluated at 1. Okay, so here we go. So 2 ways. One way, so we want the probability that x is less than or equal to 1. We know that x, the support for the random variable x, starts at 0. So that means 1 minus the probability that x equals 0 and x equals 1, right? So it would be something like this. Let me create a vector x that contains 0 and 1 as its elements. Now I evaluate the probability mass function at x. The parameter prob is 0.02. That's a probability of success. So I am evaluating the probability mass function of that geometric at 0 and 1, right? Now I do the sum, and finally 1 minus that should be the probability that I want. As you can see, it is exactly the same that we had before, right? There, 0.9604, right? Another way, since we know that this is the same as 1 minus the CDF evaluated at 1, well, there's a function, right? A built-in command in R that is going to help us evaluate the CDF at 1, right? Same thing. Okay? Okay, so let's summarize what we did here in this video. So we had this problem, this probability problem, and we realized that we could set it up as a probability problem that involves a geometric random variable, right? So first, what we did is we solved the problem by hand. We set it up by hand, and the usual way of thinking of geometric distribution is the number of trials until your first success, right? And that's what we had here. The regular way of thinking about a geometric distribution, number of trials until your first success. Okay, but it turns out that there's another way of thinking about geometric random variables, and that's the way R thinks about them, as number of failures until your first success. So we set it up both ways, and we were careful in doing the translation from our initial random variable y that gives you the probability of needing y successes to y trials to get your first success, and the random variable used by R, which is x, and it's the number of failures until your first success. And well, we were careful, and we ended up with the same probability. Okay, well, just keep that in mind. Okay, that R uses well, thinks about geometric random variables differently. Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.